The second part of Chapter 2 deals with chemical reactions in organic molecules. So this is going to be a little bit longer PowerPoint presentation, and we're going to get a little bit more detailed. First, we need to learn about some of the different types of chemical reactions. We've got 4 here. There are more. We've got a synthesis reaction, a decomposition, exchange, often called displacement reactions, and then we can also classify reactions as being reversible, meaning they can go either direction, and I'll get into that explanation here in just a minute. So I have some analogies for these different types of reactions. A synthesis reaction is kind of like a marriage. We have 2, sometimes more, but 2 coming together to become 1. You can recognize this by looking at your reactants and products. Do you remember which side is the reactants and which side has the products? Give you a second to think about that. Okay, so remember the reactants are on the left. They're always what you start with. They're the ones undergoing a reaction, and the products are what you wind up with. So you need to be careful with that and be sure you understand which one is the reactant, which one is the product. So whatever is on the left, whether it's 1, 2, or 10, is always going to be called the reactants or a reactant, and whatever's on the right side of the arrow will always be the products. And so you can see here, looking at this picture, we have A that's by itself and B by itself, and they come together and form a B. They form a compound. This could be something like sodium and chlorine coming together to make sodium chloride. Okay, so that's 2 coming together to make 1. That is a synthesis reaction. Synthesize means to make something. And then we have a decomposition reaction, and my analogy for that is it's a divorce, because it's basically the opposite of a synthesis reaction. So over here, what is this called over here? Yep, it's the reactant, and then these are the products. So this side over here, you have 1 compound. That is how you recognize it. If it's a synthesis reaction, you have 1 compound to the right of the arrow. If it's a decomposition, you have 1 compound to the left of the arrow. And again, these are modeled with 2 reactions, but 2 individual products here on this one are reactants if we're looking at synthesis, but it can be more than 2. It can be 3, and sometimes even 4 things coming together to make 1. So what you want to look for is, do you have 1 substance on either side of the arrow, and then that's going to be a synthesis or decomposition, and then you just look at which side of the arrow it is. And basically you could just take this equation here that I wrote for sodium chloride and flip it around. So you would have 2 NaCl on the left yields, and that's what the arrow means, 2 Na plus 2 Cl2. Okay, let me erase all that. A little more room. Okay, so then we also have what we call exchange or displacement reactions. These can actually be either single replacement or double replacement. Single replacement we don't have shown, and it's the same thing as this. The only difference is instead of having 2 compounds here, you would have a single lonely element. But we don't have to worry about replacement reactions in the human body because that's not what occurs. So we have what we call exchange or double replacement. This can even be called a metathesis reaction or metathesis. And so what you have is you have 2 compounds here, and my analogy for this is like a wife swap. Have you ever watched the TV show Wife Swap? Well, what happens there? You've got 2 families. The wife for each family changes places for a little while. And so if you'll look here, okay, and these are going to be ionic compounds for this. You've got A, that's 1 metal, and C is the other metal, and they actually change places. So you have A with B, C with D, and then after the reaction occurs, you have A with D and C with B. And so you've got B swapping partners and D swapping partners, okay? So that's what we're going to look for is 2 things swapping. And so reversible reaction is what I was talking about with the sodium chloride. It could also be something like water. It can go both directions. And so you would write this way. Oh, silly eraser. H2 plus O2. And you can tell it's reversible by the double arrow. And then I'm running out of room, but 2H2O. So that means this reaction can go either way. You can take a molecule of hydrogen, a molecule of oxygen, and turn them into a molecule of water or 2 molecules of water, or you can break down 2 molecules of water into hydrogen and oxygen gas. So it goes both ways. It is a reversible reaction. Reversibility of reactions is very important for the human body. This is how metabolism can be regulated or controlled in the body. Basically, if you have a mechanism occurring, you can have a reaction go one way, and then to get it to turn off, it can go the other way. And so it's really an important concept to understand here. You know, it may turn a process on or turn a process off, is what I'm trying to say. So we have different acids and bases and even salts in our body, and they're actually very important for different metabolic reactions. And they're also part of the way that we actually regulate and turn things on and off in our body. So they're really very important. We do have narrow ranges in our body. Acidity is one of those. You know, we have a narrow range of temperature that we can have. We have a narrow range of acidity that our blood can be in. So this is an important concept. Electrolytes you're probably familiar with. You know you need electrolytes, and then if they're not balanced, sometimes you'll need to go to the hospital and get IV fluids, and they will give you electrolytes. These are substances that release ions in water. And those are going to be ions like sodium and chlorine and potassium that are vital to bodily functioning. They're vital to certain mechanisms in the body. Something like potassium, if you have it too high or too low, it can cause disturbances with your heart and your cardiac function. It can even cause your heart to stop. So this is very important foundational knowledge here. So what is an acid? An acid is something that dissociates, or it will break down in water to release hydrogen ions. Hydrogen ions. Well, what is a hydrogen ion? Well, that is a charged atom of hydrogen. And hydrogen is on the left side of the periodic table, so for the most part, we consider it to be a metal. Now, that's a little confusing because it also can be hydrogen gas. It can actually be both a metal and a non-metal. Remember, I told you that hydrogen is a rebel and it breaks all the rules. So don't worry about that. But know it's on the left side of the periodic table in the top corner. And for the most part, you're going to consider it to act as a metal, okay? For our purposes anyway. And so it's going to release hydrogen ions, which is directly related to pH. It is going to make things more acidic, okay? Bases are going to be substances that release ions that can soak up or combine with the hydrogen, and that's going to be hydroxide, and that is OH negative. OH negative is hydroxide, and so they're going to make things more alkaline or more basic in the body. And so this is how we, part of the way that we can help buffer things in our body, meaning that we can keep our pH within that normal range that we need to be healthy. Salts are very important as well. These are electrolytes that are formed between the reaction between an acid and a base. So here we have hydrochloric acid, then we have sodium hydroxide, and that's a strong acid, hydrochloric acid. If you have a strong acid and a strong base, then what you're going to get is a salt and a water. So hydrochloric acid is the strong acid, sodium hydroxide is a strong base, and then we know we're going to get water and sodium chloride. And remember, I listed a few of the ions that we needed. Well, that sodium is very important and chloride is very important. So that is one way if we can have this acid-base reaction occur in our body that we have, we can form sodium chloride, or we can then also break down sodium chloride later on. So these types of things are important. We have catalysts, which are going to be very important, that are going to help influence the rate of a chemical reaction without speeding things up. And so all of this stuff is tied together with how our body functions so well. Okay, so looking more at acids, bases, and salts. So here we have what we call an ionic compound, And this is a crystal of salt, sodium chloride. This is common everyday salt. Truly, anything that is an ionic compound is actually a salt. You can have potassium chloride. That's what you buy at the grocery store. That's called no salt. It's a salt alternative. Magnesium chloride, that's Epsom salt. And so any metal and a non-metal compound is technically a salt. So this is where the polar nature of water is really important. Remember that water has a more positive side and a more negative side. It's two-faced, remember? So we have this dipole moment here, which just means the electrons most of the time are going to be concentrated up here, and hydrogen's electrons are going to be as close to the oxygen as they can get. And then so we have a tendency to have a positive side of the molecule and a negative side of the molecule, even though the total molecule still is neutral, all right? And so the way this works when it's dissolving something or breaking them down is sodium has a positive charge, chlorine a negative charge. So we know that positives and negatives are attracted to each other, right? So sodium will be surrounded by the negative side of water molecules, and that creates what we call a hydration shell. Hydration shell, because they're being surrounded by water molecules. And so it's got, what, 4 water molecules around it. Well, it's going to be much more attracted to those 4 oxygens and those 4 water molecules than 1 chlorine molecule, okay? Because you've got a whole lot more what we call electronegativity involved. There's a whole lot more protons in 4 oxygens than there is in 1 chlorine or in this case, we're going to be talking about electrons. Sorry about that. The electrons in the 4 water molecules than 1 chlorine atom. And so same thing is going to happen with chlorine. It is surrounded by water molecules, except it's attracted to the positives. And so it's going to be pulled apart and kept apart by its attraction to all of these water molecules surrounding apart. And that's what keeps these as ions in solution. I believe I said earlier that ions are really a transition type substance. They're not normally just there by themselves, that we have atoms and we have ions. That's not really how it works. You have an atom that can become an ion to make a compound. And so when we're looking at this is one of the few times where these are going to actually stay as ions. But they're not going to stay that way long, because our body is going to take this and assimilate and use them in our body. For instance, the sodium ions are really important part of sodium ion channels in things like when we look at the nervous system and we look at what we call the action potential, and we're going to have sodium and potassium ions and some chlorine ions flowing in and out, and that's what allows the nerve to transmit the signal. So these tiny little substances are just foundational and very, very important for how the human body actually works. So once these ions are dissolved in water, then we call them electrolytes. That's basically the difference. The concentration of acids and bases can affect the rate at which a lot of these chemical reactions occur in our body, okay? We have a lot of biological processes that occur within a very narrow pH range. And we actually have these neat things, and this is kind of getting off into biochemistry, but they're called Zwitter ions. And basically, they can be changed to be an acidic, basic, or neutral, and that affects their functioning, okay? You're changing the structure, and remember I've said your structure determines your function. So those are really kind of neat things, and again, it's all about how the body is going to regulate, turn things on and off, and how our mechanisms of these chemical reactions are going to occur. pH is very important for things like proteins. Why is it when you get a very high fever that it can cause brain damage or kill you? Why? Well, people usually answer by saying, well, it fries your brain. Well, what does that mean, fry your brain? How does it fry your brain? Well, what it does is it actually denatures a protein, and we're going to look at that a little bit more when we talk about proteins. It causes the proteins to break down where we can no longer use them, and that can occur with either too high of a pH or too low of a pH. And I said temperature, so I got off on the wrong tangent there for a moment. But pH basically works the same way as temperature. If it gets too acidic or if it gets too basic, it can cause your enzymes not to work. And enzymes are our worker bees. They really help all these chemical reactions occur. We could not do all the chemical reactions that we needed to without enzymes. So if enzymes are denatured, if protein is denatured, we really have some problems. We're not able to function in the way that we should. Okay, so the pH scale is basically the range that we have for pH. And pH we often call power of hydrogen, percent of hydride ions. So the more hydride ions you have, the lower the pH. So we're going to start with 0 here. 7 is going to be neutral, and 14 is going to be on the end. So this is going to be more acidic, and this is going to be more alkaline or basic, okay? And so there's some different substances on there. You can see gastric juice, apple juice, tomato juice, cabbage, milk, blood, sodium bicarbonate, which is baking soda, milk of magnesia, ammonia. So you can see the range of things from very, very, very acidic with a lot of hydride H+ ions, or very, very basic with a lot of OH or hydroxide ions. A lot of times too, people think that an acid is worse than a base. That is not true. They are both very, very caustic substances. They are very, very strong. So neutral is going to be 7, and that means you've got equal amounts of hydride and hydroxide. Acidic is going to be below 7. So if you have 6.9, that's just slightly acidic. If you have something with a pH of 1, that's very, very acidic. Okay. Same thing for OH, except going the other direction. So pH is very important again for homeostasis. Homeostasis is maintaining and keeping a constant internal environment by staying in these important ranges like pH and like temperature. The pH scale has a 10-fold difference in H+ ion concentration that separates each whole number. So it's not from 1 to 2, it's going to be a logarithmic scale. There's a very large difference between 1 and 2. It's not just a little difference. The lower the number, remember, the greater the H+ concentration, the more acidic it is. So what happens if our pH gets a little too high or a little too low? How do we deal with that? There's several different ways, but we're going to look specifically at buffers. All right, so buffers are substances that resist changes in pH. So they're basically kind of like a little sponge that can soak up those acidic ions, the H+, or they can soak up the hydroxide ions like the OH negative. So they can, to a certain extent, basically absorb the changes in pH that occur. They soak up those excess ions that are released by some of these substances. So we have buffer systems in our body which are really important. One of those is the carbonic acid bicarbonate buffer. This is part of cellular respiration, and this is how we actually remove carbon dioxide from the blood and keep it from building up too high. Have you ever thought about that? We breathe in oxygen. Well, what do we exhale? We exhale carbon dioxide. So how do we keep that carbon dioxide from building up too much? Well, we have a mechanism to remove that. The normal range for blood's pH is 7.3 to 7.45. That's a pretty narrow range, so we need to be able to keep it within ranges. And so as far as disease processes go, you can have an alkalosis, which means you're too basic, that occurs when you get to just a 7.5 to a 7.8 pH range. All right, so we need to be able to control this in our body. Acidosis occurs when it drops below the normal pH range, which you can see blood is actually a little basic normally because that's above neutral. Remember, 7 is neutral. And so if it drops down to 7.0, that's not very far, then you can have acidosis. And you might be familiar with like metabolic ketoacidosis, and this is what happens for diabetics, okay? So it's really important. So we have these homeostatic mechanisms to help regulate pH, And we have buffers, which are going to be chemicals that can soak up either that hydride ion or the hydroxide ion. They can kind of soak up those and keep the pH within a normal range. Now, there is a limit to how much they can soak up, but they do a pretty good job of it. So let me ask you, what does organic mean? Because you have a certain definition of organic in your mind. Take a moment and think about that. I'm going to pause this. I want you to write it down. Okay, did you write it down? I bet some of you did. All right. So most people, when I ask them what organic means, they think about organic food and the connotation of the word organic in everyday use. That means what? No pesticides, no antibiotics used. Well, that's not really the technical definition of what organic means. Organic means it is a hydrocarbon. It contains carbon and it contains hydrogen as its basic structure. Okay, so ionic compounds are going to be what we call inorganic molecules. These are not hydrocarbons. So these are not carbon based. These are usually things like water, soluble water, and soluble electrolytes, that type of thing. Inorganic salts. Okay, and so these are actually even two completely different studies in chemistry. You have inorganic chemistry, which is what you normally think of as taking when you take a general chemistry or university level Chem 1 and Chem 2 course, and then organic is a whole separate type of chemistry because it is based on these long chain hydrocarbons, which basically you have, let me turn that pen on, chain of all these carbons, and they're surrounded by hydrogens. And so there would be a hydrogen at the end of all of these. Okay, and so that would surround that. And then you can have some different functional groups on the end of these, and those functional groups change the structure of these hydrocarbons. And what do I say about structure? What does it determine? Well, I hope you're thinking function, because that's extremely important. Structure determines function and is directly related to whatever functional group we might tag on at the end of this molecule. We might put a C and then have a double OH, and that's not really how you would draw it, but trying to fit it in there, and that would be a carboxylic acid group on the end. And so we're going to look at those quite a bit as well. When substances dissolve in water, the polar nature of water, like we already discussed, is what's going to help separate them, often breaking them down into ions, which we already said allow metabolic reactions to occur. That is certainly not all that water does for us. It also transports chemicals through the body and blood. Things like what is in our blood? Do you know what all is in our blood? You probably hadn't really thought about it. Oxygen, sugar, salt, vitamins, hormones, all types of things are transported in our blood. Okay. So water is the most abundant compound in a living organism. 2/3 of the weight of an adult human is made up of water. It is a major component of all bodily fluids. It is the medium for almost all of the metabolic reactions that occur in our body. And it has an extremely important role in transporting chemicals in the body. It also helps to regulate temperature. It can absorb or transport heat. Okay. So oxygen, why do we need oxygen? You're probably saying, well, so I don't die to breathe. Well, that is true, but why? Why does it matter? What process is dependent on oxygen? Well, we cannot do cellular respiration, which is the basics of function of our metabolism, and we'll look at that, without having oxygen. So we can't make ATP. And what is APT? Do you remember ATP? Do you remember what ATP is? Made in, y'all used to say the powerhouse of the cell is made in the mitochondria through cellular respiration. It's the energy currency for our body. This is where we get the energy for everything that occurs in our body, all of our metabolic activities. Oxygen is the final electron acceptor in aerobic cellular respiration, and so we cannot do cellular respiration without oxygen. So that is why we have to have oxygen. So if carbon dioxide builds up in the bloodstream, it then can become toxic. So we convert it through that bicarbonate acid buffer system into carbonic acid, which is a weak acid that allows us to transport it to the lungs and expel it. How do we get carbon dioxide in our body? Well, that is a byproduct of cellular respiration. And so we have to be able to get rid of that. Otherwise, it will build up and we'll get sick. Okay. So this is the structure of carbon dioxide here on the screen. Organic salts are also very important. These are inorganic substances that are important to our body. One, if there's too much, they can make us sick, or if there's not enough, or even some, it can be either not enough or too much. Like I already said with potassium, you can be hyperkalemic, which means too high of potassium. That's what the K stands for. It's related to the word kalemic. That's the Latin. It's not the Latin name for potassium, but that's derived off the Latin name. If it is too low, you can have hypokalemia, too low of potassium, and that's going to really affect your heart functioning. So these ions are going to be very important for metabolic processes and also for water balance in the body, which is very important. These can affect nerve and muscle functions. A muscle contraction is dependent upon calcium ions. When these are out of balance, it can often be life-threatening. Like I said, potassium can, if not in the right amount, can cause you to have a heart attack if it is too low. So again, these are very important ions or electrolytes in the body. These are inorganic substances. Some more important organic substances are carbohydrates, which you probably know what a carbohydrate is. We associate that with bread or a sugar. Our bodies are very, very busy and they need a lot of energy. Carbohydrates provide that energy in a form that our cells need, as well as materials that we need to build different cell structures. They are often water soluble. They contain different ratios of carbon, hydrogen, and oxygen. It's going to be close to 2 to 1 for most. So you see here C6H12O6. So the ratio will kind of stay the same, but then the number of these that are put together is what changes. So these are classified by their size. We have a monosaccharide. A saccharide means sugar. Mono means one. So these are going to be your simple sugars. That's going to be things like glucose and fructose. And this is a picture of glucose over here. And this is fructose. So you can see they're very similar. And they are one molecule. Okay, one sugar. These are very simple, easy for your body to break down and use. We also have di. What does the word part di mean? Di means two. So saccharide, sugar, so two sugars. So this is where two sugars are joined together. And so we will put two of the monosaccharides together to make sucrose and two of the monosaccharides together to make lactose. And then we have what we call polysaccharides. Poly means many, and so these are going to be very large polymers or macromolecules, if you want to call them that. Many joined together, okay? That's going to be like glycogen and cellulose. And so you can see that here. This is the picture on the bottom. These are much more complex. So if I took two of these right here, that would be a disaccharide. If I took one, that would be a monosaccharide. All of this together, you can see it's very, very complex, and that is a polysaccharide, and that's going to be like cellulose or glycogen. These are just some different structural forms that you may see glucose in. These are really used a lot in organic chemistry, and they have different purposes for the way they're done. But you can just kind of see the basic structures here. Remember, structure is important. Why? What does structure determine? Yep, you get it right. Function. Here we can see a little bit better the different size of our saccharides. Up here we have our monosaccharide. You can see that it has one ring structure. That's one carbon, hydrocarbon. Then you have your disaccharide. It is going to be two of those 6 carbon rings joined together. And then here is a polysaccharide, many of them joined together in a complex structure. And these are what we call our complex carbohydrates. We tend to associate those as being a little bit healthier for you, because you can imagine it's much easier to break down this big molecule than it is. You got one link there to break, and look at all the links you have to break on that. There's a lot. So that's why they're complex carbohydrates. They are digested slowly. Cellulose is interesting. It's a polysaccharide that is abundant in plants. The interesting point about that is humans cannot just digest cellulose, and so we call that dietary fiber. Lipids are important. These are organic compounds that are insoluble in water, and these are part of the four macromolecules that we'll look at that are really important to the body. Okay, lipids is one of those. Carbohydrates is another. And so lipids are organic compounds. They're insoluble. They have a very, very important job in cells, and they are a very important component of the cell membrane. And you should have been or currently looking at cells, and so they're part of the phospholipid bilayer. The most common type of lipids that we have are fats, and we commonly call those triglycerides. Fats supply energy that is vitally needed for cellular activities, for our cells to function. Fats can supply more energy than carbohydrates can if you look at the same amount. So get your bang for your buck, the most bang for your buck, fats are going to give you more energy if you have like a gram of each. Okay, so you can see here, looking at the chain, that these are hydrocarbons. You can see you've got all those straight chain carbons in a row with all the hydrogens here, and then on the end is that functional group, and that's the carboxylic acid I wrote on the other page that I told you I didn't really write in the right way. That's a carboxylic acid functional group. Now, these are two different types of fatty acids here, saturated and unsaturated, which you've probably heard of. The building blocks for a fatty acid are going to be a glycerol, or for a lipid, I should say, and 3 fatty acids per molecule. 1 glycerol and 3 fatty acids per molecule. We'll look at those. Saturated fatty acids, as you can see, they're straight. They're not branched. Okay. Unsaturated fatty acids are branched, and you can see here there's some double bonds. This is why there's a double bond there and a double bond there, and that causes the molecule to turn and branch or kink. Okay. So a saturated fatty acid, and that's the one on the top, stack up really well. Unsaturated fats, because of their kinks, so if you think of it this way, you've got your fatty acids. They're going to stack up nice and neatly. Unsaturated fatty acids are like this. So can you imagine trying to stack those up? They don't stack up as well. Okay, they're kinked, or what we call branched, which is related to why some are healthy and some are not healthy. Okay, and so the main difference is they're going to have that double bond here. Lipids are, of course, the fats. They're insoluble in water because they are a non-polar substance. So if you look at the basics here, you know, a polar molecule, remember, had a positive and a negative end. Okay, well, a non-polar molecule is very symmetrical most of the time, and it's kind of the same all the way around. They don't change. They're not positive or negative. They're stable. So this is that good friend that you can always count on. Okay, remember, polar molecules were kind of like two-faced. They had a positive side and a negative side. Well, this one is just that flatline person that's just always happy. And so you have, and this is a horrible drawing, I apologize, I'm having to use this pen, but you've got carbons and hydrogens all the way around, and you can kind of see that structure here, okay? And of course it's bonded to a carbon there, but if you put a hydrogen around it, it'd be the same all the way around, okay? There's not a more positive or more negative end, and these two just don't mix. This is why oil and water doesn't mix. Oil is non-polar. It does not have a positive and negative side, and water is polar. It has a very positive and a very negative side. So saturated fats, remember, have that glycerol, and that is going to be this portion over here. Oh, it's there. And then 3 fatty acid tails. And so each one of these are a fatty acid. That's the 3 fatty acid tails. Saturated fatty acids are going to be the unhealthy type. They can cause atherosclerosis, which clogs blood vessels. Unsaturated fats are healthier: olive, canola, macadamia nut oils. Saturated fats tend to be more solid at room temperature. These, like butter, lard, or animal fats, so they typically are the ones that come from animals. Unsaturated fats are those that are going to often be liquid at room temperature. So like canola oil, that type of thing. Olive oil, those are healthier. You can also have what we call hydrogenation, and that is what we call a hydrogenated fat. And so this is a food processing technique. Oh, I forgot to say unsaturated fatty acids do come from plants. I may have said that. Anyway, hydrogenation is a food processing technique that adds hydrogen to unsaturated fats, which make it more solid and therefore more useful in prepared foods like margarine. But that makes it much more unhealthy, because some of those double bonds are changed to single bonds, and that makes them trans fats. And basically, trans means they're on opposite sides. So if you had a molecule and this isn't going to be a trans fat example, this is just going to be an example. We had chlorine on the same side attached to those. That would not be trans. If we moved those, and they were on opposite sides of the molecule, usually it's going to be diagonally, then that would be trans. Okay, so trans means on opposite sides, and so that changes the structure of things. And remember, we said structure determines functions. So when we change the structure of things, we are changing partially how they function. So that's very important. So they change some of those double bonds to single bonds, and they're really just making them much more unhealthy, unfortunately. So that's why you want to stay away from trans fats. It's going to increase the risk of heart disease. Okay. And so these fatty acid tails here on this molecule can have different lengths, and they can have different levels of saturation, and that's why we have such a different diversity in all the different kinds of oils and fats that we can buy and use and that we eat. So phospholipids are pretty similar to fat molecules. The only difference is they have 2 fatty acid chains instead of 3. And then they also have a phosphate group. The phosphate part is going to be water soluble, and it forms what we call the water soluble hydrophilic head right here. This looks like a little guy with legs. So the legs here, those are going to be the fatty acid chains. And then we have the phosphate hydrophilic head and hydrophobic tails. Hydrophilic means hydro means water, philic means loving. So that's going to be the polar end, and it's going to be water loving. Hydrophobic is going to be, because it's fatty acids, the nonpolar end, and it is going to be water fearing, so it doesn't like to be around water. Okay, so this is really, really important to how our cells and our phospholipid bilayer of our cells is constructed. Okay, it forms that phospholipid bilayer. It's a major component. It's a protective layer for the cell. Okay, so major component here of cell membranes. Another type of lipid that you would not think of as being a lipid is steroids. When you hear the word steroid, what do you think of? You usually think of things like anabolic steroids that people use to build muscle, or steroids that people take when they're sick, but they're really much, much more diverse than that. These are complex structures. They form ring structures, even though these don't look like a ring because they are geometric. Those are what we call rings, or silics in organic. They are complex structures. They form things like cholesterol, sex hormones like testosterone and estrogen, adrenal hormones, lots of other different things. So these are very important, and they're widely distributed in the body, and they have lots of different functions. They are a component of cell membranes. Cholesterol is found in the cell membrane. That's what tends to give it a little bit more firm structure.